Yeah, well, people will be coming by. Yes.
Well, let me see if there's some people move to the coffee machine.
No, I want them.
All right.
That's great.
All right, everybody. So good morning. Welcome back. So today we're starting our session with Daniel POLANI. Daniel is right now at Hertfordshire, where he is at the Department of Computer Science. And Daniel has sort of built a track record on really taking a bit more also a formal perspective on complex phenomena, including robots and humans and other things, with also the idea that if we have these more formal approaches, we have more power in terms of our prediction and control and what have you. So it's not only from a pure, let's say, mathematical or applied math perspective, it's also in terms of then translating basic principles and phenomena to control of real systems, or real world systems, right? So I think it's a very unique position in this sort of link between control of robotics and math, and also another expression that Daniel is also one of the members of the Socializing Sensor Motor Contingencies Consortium. It's one of the co-sponsors of this event. Daniel is also involved in the RoboCup community for basically since its beginning, since its inception, and which is playing a very important role in the field. Because as you know, in robotics, I know you ever went to a robotics conference, but I find it usually annoying because you have people that they show you very quickly because there's no time. They show you some equations, and of course no one can understand them fully because there's no time to discuss. And then they show you a video, and in the video something happens. And the something that happened is supposed to be related to the equations you saw before, and then that's it, you have the next talk. Okay? And so that means this makes robotics rather different from science, if you want. In empirical science, if we define science as such, it's always nature and the real world that is your benchmark that everybody converges upon. So you can have some stupid idea about consciousness, let's say, even though everything I share with you is true. In the end, the experiment decides, and we all agree, if your prediction is not supported by the empirical evidence, then that's it, it's dead, right? And in robotics, these kind of benchmarks are actually lacking. People are just sharing videos, and they look very cool. Because the one time that worked, at least 10,000 attempts that they had. So what Daniel now is going to lead, he's going to be the president of this organization next year. He's president-elect right now, so we're in the presence of a president-elect, which certainly in this day and age, 2016, elections coming in the States, is an important moment, so we should wear t-shirts, vote for Daniel. Of this organization, RoboCup, that actually tries to improve the situation in robotics. We say, let's at least have benchmarks we can compare our approaches to, that we have a common, if you want, also empirical validation of what the hell we're talking about. I think this is really important. Of course, we can have many discussions about what's the right benchmark, but it's really important, and it's also fantastic that Daniel's going to be spearheading this into the future, and also rethink how can we, if we build these artificial systems, robotics, living machines, how can we actually really benchmark them in such a way that we also know that we're making progress? These are very important questions that Daniel is dealing with, so it's great he's here with us. He's going to be here till the end of the workshop. So thank you very much for joining us today and in the coming week. I'm looking forward to his talk, which will be on the informational principles of embodied cognition. Daniel, thank you.
Paul, thank you very much for inviting me. It is a great pleasure, and also Anna for handling all the bureaucracy involved with that. I had all these special requests, request 1, request 2, and 3, 4, 5, 6, and she handled all of them. Thank you for that. I really appreciate it. Being now more of a paper pusher, I know how much work it is to actually make things work. Science, believe me, is fun and it's easy compared to bureaucracy. So if you think science is difficult, well, try bureaucracy. Science at least has a way of doing things. Bureaucracy, as Marie von Ebner-Eschenbach said, is the art of making the possible impossible. Okay, let me start with the talk. I'm going to talk about informational principles of embodied cognition. And every word counts here, except for the word of. So I'm going to talk about information. I'm going to talk about principles, embodiment, and cognition. And I want to argue as Paul already introduced, that there are ways of looking at cognition which are not as subjective. Cognition is a very wide field. There's lots of very, very good research. The problem is very few people agree on what is actually universals there, and people have very different views of that. And I want to convince you that there is a relatively unified way of looking at it. There's a suggestion of a unified way of looking at that can help us understand what's going on. But before I do that, I would like to give thanks to a huge amount of people which worked with me over the last years. Alex Klubin, who did the perception action loop, essentially relevant information, is joint work done in Lübeck and in Hertfordshire. Digested information, continuous empowerment, and many, many other people who have contributed to this work. Some of them PhD students, some of them postdocs, some of them colleagues. Okay, can you all hear me up to the last row? Yes? Yeah, you can. Good. Unfortunately, they forced me to wear a micro because otherwise, with my own voice, I know how far it reaches. But with a micro, I have no idea. It's always a guess. So let me give you a crash introduction on the motivation for this type of perspective. And why I'm saying crash introduction, it has grown out of a tutorial on sensor evolution, which I used to give. And this sensor evolution tutorial was used to be 3.5 hours length, and it was quite exciting actually, because once you start looking at what sensors evolved in nature, you start getting sucked in. It's incredibly fascinating, and I will give you the 3 minutes version of that. So the question we are asking is, how did cognition evolve in biology? And this is an interesting question, a very deep question. If you're not a creationist, because then you are not interested in that, because you know the answer. But if you are basically believe that evolution generated cognition, then we have to ask ourselves, where did cognition come from? And an interesting indicator for that is the following observation. If you go into biology, it turns out, and this is kind of the really short version of my sensor evolution talk, that sensors in evolution are highly optimized. Highly optimized, for example, there are moths, night moths. These moths can detect individual molecules. That's what anecdotal is being said. It's not true, actually. It's few molecules. Few means a couple of hundred. Okay? The best quote for that I found in Dusenberry, and he says 200 to 300 molecules of that particular pheromone. The individual molecule story is not something I can currently confirm anywhere in literature. I'm not saying it's not true, but I didn't find any source for that. So few molecules, 200 to 300, that's not a lot. It's very few. We can do better with photons. Photons, humans. You take a human, you put him in a dark room for several days. Say, for example, could be an astronomer or could be a prisoner, doesn't matter. But at the end of this experiment, they can detect a handful of photons. Handful means 10 to 20. This has been shown. And there are toads, actually, that can detect even individual photons. Single photons. That's as good as it gets. You cannot become better than that. Now, the interesting point about that is that if you have essentially this, it means that you're operating at the very limit of what's physically possible in terms of sensoric detection. You do not get better than that. Also, the auditive sense, it operates close to the thermal noise. So if you're listening in very silent rooms, little kids can detect noises that are just above the thermal noise. Now, I have to say that it holds only until the first time you go to the disco, because after that, it's done. But, you know, this is kind of what we are being equipped from nature. Now, that means that if you have such a sensor, why are you at this very limit of performance? It gives you an indicator that our sensors are tuned to go to whatever they can extract in terms of information from the environment. They go to the very limit. Now, the funny thing is that cognitive processing is very expensive. Very expensive is very expensive in the sense that your brain, for example, in its quiet rest state, eats up 20% of your metabolism. 20% if you don't do anything, or you watch EastEnders or whatever telenovela happens to be on your screen. So 20% for nothing, right? So the lamp that glows over the head, but on the other hand, it's not much. The lamp that glows over the head of you know, these cartoons when they have an idea uses more wattage than your brain. Nevertheless, 20% is a lot, is a big tax, and when you start thinking, actually, then the cognitive processing becomes even more expensive, 40%. Goes to 40 to 50% of your whole metabolism. So those people who said sport is mostly mental, they are right. You don't have to move, you can burn up a lot of calories. Okay, so that's what the way I like to live. No sports. Anyway, so the motto we have, despite the fact that it's very expensive, we want all the information we can get. That is interesting. So the motto is capture all information you can get. Let's have a look. Well, what you can afford to get. Not everything that you can, in principle, get, you can afford to get. There's a difference here, because it's expensive to actually reach out and get this information. So let me summarize this observation. Sensors operate at physical limits, but we have at the same time, obviously, a cognitive pressure for higher evolutionary functions. It's not entirely true. You can live very well if you are a sponge or a bacterium. You don't need a big brain for that. But we have quite a big niche of animals, well, comparatively big niche of animals that have a big brain. And it's not just a human. For example, the octopus. My favorite animal is the octopus, and not on the plate, but actually the living one. And the reason for that is that the octopus is evolved in a completely separate branch of the evolutionary tree from mammals. And nevertheless, it is a highly intelligent animal. And the interesting point, if you watch the octopus, he doesn't like to talk a lot about his family members because they are mussels and snails with just a few neurons. Right? They're not very, educated. But the octopus himself is herself is a very highly intelligent animal. And it's estimated that the intelligence level of an octopus is around the level of a cat. That's pretty high up. In the letter, we don't exactly know, they're not identical. But they have a cerebellum-like structure. Their eyes are actually better designed than ours. The retina is on the right side. It's in the front, not in the back of the blood vessels. So the octopus is really, although the evolutionary tree split off from us 500 million years ago, that's a long time in terms of multicellular evolution. Multicellular evolution, not single-celled. Single-celled evolution is much older, but multicelled evolution is really, really a long time. Nevertheless, they co-evolve, they converge to something that we all consider highly intelligent. In other words, we have two instances of intelligence evolution, or evolution towards cognition, high cognition. Now, I'm quoting Ilya Neimanman, who said, if you have 0 events, you have no statistics. If you have 1 event, you have no statistics, but you have 2 events, that's statistics. So 2 events is already significant. If we found life in the universe twice, that's significant. Once, we don't know anything. So what do we need the high cognitive functions for? Well, the point is, we talked about sensors, we talked about brains, but we need actions, because that's what ultimately matters. If you look and watch and think and reflect, but you do not act on it, never act on it, it's irrelevant. It's completely unimportant. So actions matter, or as the Germans used to say, or the German Chancellor Helmut Kohl, who was not considered the most intelligent. He was our W. Bush, kind of, in a way. And he said, entscheidend ist, was hinten rauskommt, which is, I'm translating, important is what comes out at the bottom side. Which is, from a guy that looks like a big baby, an interesting statement. But he's probably right. It's essential what comes up at the end, right? So it matters what happens at the end. And so actions matter. So unless you transform your process sensoric cognitive processing into actions, it doesn't matter. That is kind of the philosophy that I'm trying to embrace here. So being a Platonic entity that sits over the waters, hovers over the waters, looks at the world, thinks, reflects, but doesn't do anything, doesn't matter. It only matters when it interacts in the world, and of course, that is what we call embodiment, or is part of the story of embodiment. It's not the whole story. We'll see later that there's more subtlety to it, but it is part of the story, the essential part. So let me look at the trade-offs. Sharpening sensors. Can you get better sensors? Okay. Shall I invest in better sensors? Shall I improve my brain power, my memory, my inductive power, Sherlock Holmes, whatever? Or shall I improve my actuators? So let us ask the question, where is the investment best done? We can say, oh, I'm brawny, I have big muscles, I don't need to think a lot. Let's take the example. This guy goes into the bar, and he just moves on, everybody moves out of his way. If you're a small guy, you don't do that, right? You try not to bump into people because, hey, do you want something? Well, I live in England, and Saturday nights, that's what happens. So boosting actuators can have an advantage, but now I'll give you a scenario where it doesn't. So you are an antelope, and you graze in the savannah, and suddenly you see the lion comes up, just here, because you didn't notice him. That's a bad thing, because now you have to run really fast. You should not stumble. You should really do the right movements. You should not fall down. It's really dangerous, and at the end of the run, you're completely exhausted. So if you come in another difficult situation, you're in trouble, right? So you need very, very fast and reliable actuators for that. On the other hand, if I'm an antelope in the savannah and oh, there's a lion. I'm seeing the lion something like half a mile away. Say, let's move away. Slowly, slowly. You move away, you get out of danger, nothing happens, you are safe. So you saw the danger ahead of time and kept it from exploding, okay? Same thing as if you have a good sensor that measures your engine before it breaks down and says, well, the motor is overheating, stop it, or fix it, or exchange it, you save a lot of effort later. Good sensors can prevent an exponential buildup of trouble, if you like. So in other words, all those sensors are expensive, and processing is expensive. They are probably much cheaper than boosting your actuators, or making bigger and more heavy machines, because you just prevent trouble that you would have otherwise. And the trouble grows exponentially. Well, kind of in a way of saying it. It's not always exponential, of course, right? So investing into sensors can offset having bigger actuators. So let's have a look at what we need to understand sensors. And the term is information. Right. So what we are going to look at is we are going to link sensors, the processing we do with whatever sensors pick up, and the actuators. So I would like to plug into what Paul said earlier. We slightly steal stuff from physics in a way here, because the philosophy that physicists have, they say, well, you have a given dynamic equations, and in principle, once you know them, and most of them are known, not all of them are known, but most of them are known, we can start to compute stuff. I mean, practically, that can be very difficult, but de facto, when we assume they are known, everything is essentially done. It's agreed upon. We're not talking about dark matter and all that stuff. That's kind of interesting, but not clear. I'm talking about the standard physics that we all know, Newton and the basic Einstein and so on. In biological cognition, that's an entirely different ballpark, because here there is no established unique model, and it's complex and difficult to untangle. And I would like to emphasize, opposite my office sits a very smart guy, one of the world experts on the cerebellum. He had the visit of another extremely smart guy, also one of the world experts on the cerebellum. And I witnessed them in a table conversation, breakfast table conversation. And one says, yeah, the cerebellum does this and this. And the other one says, no. The cerebellum does this and this. Now, these are two of the smartest people in the field, and they disagree on what the cerebellum is doing. That should tell you something, okay? It tells you, not that they are wrong, perhaps both are right, it's quite possible, but we do not actually know how it works. And in fact, if you look at robotics, I mean, Paul mentioned RoboCop, we find that you can have two teams that perform nearly identically on the field or in the game, and they are completely incompatible in terms of code. You look at the code and there's no way you can fit them together. You say, oh, this was a good movement. Can I have your movement routine? And you can't plug it into your code because there's no way to plug it in your code. It's completely coded in a different way, in a different philosophy. Basically different brain wiring. Okay? So you have nearly equivalent but completely incompatible solutions and architectures. And what's worse, there are specific in-hand designs. So there's not some solution. I say, okay, this is what you do, and then you let it run for a month, and then you have a robot playing robot football. No, you have a team of extremely smart people coding and doing, oh no, we do this, we do that, and they come up with their solution. And it's very specific, and it's not generalizable. So the question is, how can we overcome the arbitrariness in the treatment of cognition? If I say, oh, I have this and this architecture, or this and this architecture, the question is, what's universal about a particular cognitive architecture? Is there some way of making a cognitive architecture understood without saying, this is the only way it can work, or these are the 3 or 4 or 5 different ways in which we can formulate them? And so this is my wish list. What I'm putting here is the wish list. I would like to treat cognition uniformly. So one size fits all. Not one size fits all, but one language fits all. It's not one size I'm going to promote. I'm going to say there's one language that we can apply to most of cognitive phenomena and get statements, get predictive statements about that. And I would like here in this language to distinguish the essential. This is something that this process must do to be performing, versus the incidental. This is, well, could look this way, could look another way. Octopus, right? The retina in the octopus is in front of the blood vessels. In our eyes, the retina is behind the blood vessels. So the octopus got it right, but ours works too. Okay? It works. So can we do that? Well, I would like now to give promote the physical picture of these things, the covariant modeling of computation. Covariant modeling of computation. Think of it the following. Don't have a stick, so I'll take just this bottle. Think of it as a vector. You look at this vector. This is a physical object, and if you look at this vector, you see this thing. Nice. It looks like okay, nice. It points that way. And now I'm moving here. Oh, it looks different. Okay. Is that the same object? Is this a different object? Well, of course, we know it's the same object, but we know how to change this perspective to this perspective if I make this movement. That's what we learn in physics. In physics, we learn that same objects are the same object can look differently depending on how you look at it. And in fact, in physics, they have brought it to a high art. This is called basically a so-called covariant picture. Covariant picture is a picture where you know exactly how it looks different from different perspectives, describing the same type of concept. Now let's ask, can we be covariant in cognition? What we're saying is that particular computation may depend on the architecture. Yes, the computation itself will be different on an iPhone processor or on a Samsung or on a Nokia or whatever, but the concepts computed are essentially the same. This is what we are trying to see. So in other words, I will use the physics language here. I would like to have a coordinate or a mechanism-free view of cognition. Cognition where I'm not looking at how it's actually computed. I do not care whether it's a brain or fly brain, human brain, octopus brain, a computer, alien, quantum, whatever. I don't care. I'm asking, is there something fundamental, identical in a particular cognitive view? That's what we're trying to do. This is the motivation for what we're doing. So our hammer is information, and we'll use it on everything. Okay? So if something doesn't fit the language of information, we'll make it fit. Or as they say in German, was nicht passt, wird passend gemacht. What doesn't fit will be made fit. Okay? Okay? So if something doesn't fit in our language of information, we will squeeze it until it does fit. Okay? Think of it as a translation. It's a more friendly way of putting it. But I wanted to be really drastic because that's what we do. Just so that we are all on the same sheet, because not all of you have seen perhaps information theory. I don't spend much time on that. This is not a course on information theory. I just give you the notions so they can pick them up and then we can discuss them later. I'm actually here around until the end of the next week, until the end of the summer school. So please do contact me if you have questions. That's what I'm here for. So that's, we define a few things. We have random variables. They can take values x, y, z. And the sets they come on are written in calligraphic notation. We will notate probabilities in this way. So P of when the variable x takes the value little x, or we'll write that if there is no ambiguity, P of x. Then joint probabilities is the probability that capital X gets the value small x, y gets a value small y. This is also written here if there's no ambiguity. And finally, conditional probabilities will be written like that. So the joint probability is nothing else than the probability of x times the conditional probability of y given x. This is a standard Bayes rule. This is the first notation. And with this, we can write the most important notions we need today. Entropy, why is this value the entropy? Well, I don't have much time to describe it, but think of it as the following. You see P of x, a probability that an event x happens, log P of x, or actually minus log P of x. Minus log P of x is the coding length that you need optimally to encode an event with the shortest code you can do on average, that if the event has probability P of x. So it only depends on the probability of P of x. It does not depend on what x is red or green or blue, or whether it's going up or going down. Doesn't matter. X is an event that happens. The probability of x determines the code length, the optimal code length, which is minus log P of x. And if I average over that, I get h of x. So h of x is the average length of code I need to encode some occurrence of some event. Why this? Well, it's a long story. I don't have time to explain why all this theory makes sense and why let's put it this way. Let's make a very blunt statement. Information theory simply has the most theorems. Okay? Has many things that are linked to it. There are many combinations. There are many ways of getting to this. It's like Rome. All ways lead through these set of formulas. Basically, that is kind of the 10-second statement. The story is much longer. There are many, many reasons to do that, but I don't have time to explain that in more detail. One way, just for you to get an image of what could be, say if when you make decisions, say you sit on a road, it's a black, dark road with lots of fog, and you can't see, does the road go to the left or to the right? And now you observe the road and get more and more evidence that it may go to the left. At some point you make the decision, you can say, now I'm going to the left. This evidence accumulating process can be modeled by acquisition of or reduction of entropy or increase of certainty. So entropy is like uncertainty, is how much you don't know about a process. And when you reduce that below a certain level, then you make your decision. So think of it as decision-making is something you have a threshold, you accumulate evidence, the puff, now you make your decision. Accumulating evidence can be seen as reducing uncertainty, or as we will say, entropy. Okay, that's a 5-minute motivation. I can do the same thing for the joint entropy, and you already find that I have here a printing error. It should be px, y, px, y. And I basically sum over all possible joint events. Finally, what we need is the following thing. Conditional entropy. What's conditional entropy? If I have a given x, then a variable y depends is conditioned on knowing that x is x. And then when I do that, I can get the so-called conditional entropy, which is nothing else but the entropy of y if I know that x has a value. And I can average that over all the possible x's. And I get this thing here. This is just so that you are in the picture. And the most important quantity we'll need today is this. It's the mutual information. The mutual information tells you, if I have an uncertainty about y, this is what I don't know about y. It's kind of the coding length, the effort of encoding an event in y. Then, if I know x, this coding length goes down because x can help me to resolve several bits of y, not all of them. If that coding length goes down, the amount by which it goes down on average, is always an average, is the mutual information of x and y. Mutual information means how much does x tell me about y. Funnily enough, it's symmetric. So y is as revealing about x as x is about y. This will play a role later. It's not asymmetric. It goes both ways. It's an important statement. We will see later why. Okay, so this is the quantity we need, and now we'll start moving on our stuff. So I just wanted to mention so that you know what formulas I'm talking about. It's not just in the clouds. We want to use this as a unified approach to the perception action loop. And we will use Shannon information. By this, I will mean the mutual information I just mentioned as a universal currency. Will be used everywhere, paid everywhere, not just in Europe, also in the US, also in China. Yeah, so it's much more universal than the euro. It's an info. Sorry, that was, or neuro. No. Anyway, so it's a bit. We are going to pay in bits. And we will treat it as a first-class object. It's the object of discourse. Information is what we're talking about. And we will abuse it as a coordinate-free or covariant treatment of cognition. And yeah, let's show you how to do that. I spend a lot of time on this motivation because this is the hardest part for most people to digest. Right? Going through the examples, you understand why the examples work and so on. But the point is that many people come from engineering. For them, information theory is a theory of communication and communication only. You have a sender, you have a receiver, you send a message over a channel. That's all what they think about because that's how Shannon introduced it. It was a very smart and very important move, but you can do much more with that, and that's what I'm trying to convince you of, that there is much more that you can do with information theory, not just communication. Let us ask, why should it work at all? Okay, so what are the principles that we're getting? We get invariance and minimality conditions. I will show you some of them. We can use it as so-called informational Carnot cycle. Physicists among you, or people who have been exposed to thermodynamics, know that one of the big progresses of physics was to have the Carnot cycle. Sadi Carnot developed theory for steam engines. And in the steam engines, he looked at an ideal steam engine that would expand and then create work and then cool down again. And you would heat it up, and it would go through the process of expanding and shrinking and contracting and create work by that. And he could derive some general rules of how that would happen. And what I'm saying is, think of it as the same way, but in terms of information processing. Right. Okay. So that's what we need, and I think I've said enough on that level that we should move straight to an example, and we'll start with the very first example. Actually, it dates back to the very first beginning of cybernetics. That was in the 40s. In the 40s, you see, people had not yet agreed upon what would be the right way of talking about electronic brains. What is an electronic brain? People didn't know. You had the von Neumann machine, computers as we know them today, or cybernetic machines. So you plug some wires together and something happens. Think analog computers. Think Gray Walter's devices. And one of the greatest cyberneticians of this time was Ashby. And Ashby basically had various, the papers are interesting to read. They're a bit hard to understand today because people have moved on. But actually it was quite interesting. One thing that he considered was, he said, only variety can destroy variety. So you have a world. In this world, there is some uncertainty, objects standing around, or you don't know where you are. And if you want to reduce that uncertainty, you have to invest information processing, we would say today. So only have enough variety in actions and in effects of your actions, you can actually create order in the world. If you're confined, shackled, you can't move, there's not much you can do in the world. You cannot even get it into order. And there is an extension which is relatively recent by Touchette and Lloyd in 2000-2004. And this is a theorem. It's a mathematical theorem, so it's always valid. Let's have a look how it works. Let's assume you have an open loop controller. An open loop controller is a machine that is blind and does things automatically, so it doesn't have a sensor. What is important about that is that that doesn't mean that the machine is useless. You can have open loop controllers that actually do stuff. There are many examples for that. You can have, for example, a machine that, for example, moves against the wall and then bumps into the wall, and you know that machine will be at the wall at the end of the process, right? It's not very interesting, but there are quite a few machines that are open loop and still work fine. It's okay to have them. So such a machine can reduce entropy of the environment. It can create order in the environment. And let's assume that the machine, when started, has an entropy, and at the end it has a lower entropy in the environment. And so you get a delta H, which is a reduction of entropy in the environment that the machine does. Now let's look at the best the machine can do. So say you have a machine that you have old children's toys, and now you have a set of little robots. And what these robots do is nothing else but just move straight. They are open loop. They move straight and no sensors. They move straight, and essentially you throw these robots into the room and they push the kids' toys to the wall. Stupid example, but I don't come up with, I invent an example on the fly. So they push them all to the wall. So you can ask, okay, what's the best strategy for my open loop controller to do so? And we put a star on it when it's optimal. So this is the best open loop entropy reduction. The question is, so this is kind of a Bayesian network that shows it, how it operates. Does somebody not know what a Bayesian network is? If you raise your hand, I will just explain it. I will not take you out and ask you.
You have to first ask whether they can raise their hand at all.
Oh, right. Can you raise your hand? Are you able to raise your hand?
Okay.
Yeah, most of them. Okay.
Okay, good.
So, does anybody know what a Bayesian loop is? Bayesian network is? That's a better question to ask, because not everybody raises their hand.
Exactly.
Thank you for.
So now you have to subtract the 2, and now you know.
I know there are some people who are afraid to ask, to say.
But
okay.
Before we do that, Daniel, one thing. If you say max entropy reduction with your open loop controller, that's an assumption.
Yes.
Okay.
Yes.
Just
We
be
will say.
clear about it, right?
Well, yeah, we have not said anything about that. I'm going to say a statement. The theorem will be referring to that.
Okay, good.
Will be referring to.
Yeah, sure.
Yeah. So this is the open loop controller. Let me explain how it works, because we will need this type of diagram a lot of times. So a Bayesian network is essentially a compact way of writing probability distributions in a clever way. So the way to read it is the following. These are random variables. So W is a random variable, W t minus 3 is a random variable, A t minus 3 is a variable, this is a random variable, and so on. And the way to read it is the following. This is a random variable which has a probability associated with it. So it has probability P, A t minus 3. There's a probability of this random variable having some value, which depends on nothing else because there's no arrow leading into it. Here, on the other hand, this is a random variable, Wt minus 2, which is conditioned on this and this. So the way to read these two arrows is P Wt minus 2 given Wt minus 3 and At minus 3. This is how you read it, and it's basically multiplied by these probabilities. So this thing is like a huge probability distribution, but the cool thing is you can read it. You know what it's saying. And what is it saying? It is saying that the world at t minus 2, at time t minus 2, depends on the world on the step before and on the action of our open loop agent. Yeah? So the agent does something which doesn't depend on the world. The world has some state. The agent does something. You have a new state. Now where the agent again does something, doesn't depend on the state of the world. But what happens, of course, in the world depends on the state in the world beforehand. Okay? Because, of course, whether this moves to here or to here or to here depends on where it was before. Okay? The action doesn't, but the world state does. Right. So this is the open loop controller. No surprises here. And now comes the theorem. If I close the loop, so I'm permitting the agent to look at the world, So here the action now depends on the state of the world beforehand. So I'm allowing to peak in the world. Then we can show that the entropy reduction in the world of the closed loop controller, of the better controller, the controller that allowed to peek into the world, cannot be bigger than the optimal open loop reduction plus the information that the agent gets from the world. So what does it say is that whatever you do with a blind agent, you can never be better with a closed loop controller than the amount of information you take in every step. You cannot be better than that. It's an upper limit. It doesn't mean that it converts all of it into value. So this actually, even if you peak in the world, maybe you can't get better at all. Yeah, but this, you can definitely not be better than that. That's the point of this theorem. So this is a hard theorem. It's the first theorem, essentially, of if you like, actuated or perception action loop. And it's not a physical theorem. It doesn't depend on physics. It really just depends on mathematics. This is really cool. This is hard theorem. It's a cognitive theorem, if you like. It's a hard limit on cognition. But we can do better.
It's true when the system has no memory, right?
Yes. Yes. If it's memory, then I assume you could treat the memory as a world, and then you can estimate that. Mm-hmm. Yeah, you can do better.
Exactly.
Yeah, but we can do better than this too. This is an inequality. Now I'm showing you an equality for a particular system. This is a system. It's an incredibly boring system, but the cool thing about this boring system is you understand exactly what it's doing. So we're going to look at a navigational task, and this is a navigational task. So we have a world, there's a chemical distributed, there's some spot of chemistry here in the middle, and the chemical is weaker. We're going to place an agent somewhere in this world, and the agent sits whatever on a cell, and the agent can go up, right, down, left. That's where the agent can go every step. Cannot stop. This is not really important, but I'll mention it here. It has some consequences later. The agent cannot stop, and what it's doing, it's wired to follow the highest value of the gradient. So it's basically going to the direction where the chemical has the highest value. So here it will go here, then it will go here, then it will go here, then it will go here. Sometimes if it's ambiguous, it will randomly pick one of the directions, and so on until it ends here. It can't stop, so it will always move a step out and step in, step out, step in, and so on. That's what the agent does. So it moves into the center, then wobbles around the center. Good. Now, this is a very, very, very boring system, except if you look at the informational balance of that, it's actually quite interesting, because you now can do the following. You can write a perception action loop, and I really wrote it now in the full form, but we will reduce it in a second. So remember, this is our world at time t minus 3. This is a sensor at time t minus 3. And now I introduced exactly what Paul was talking about, namely a memory. Think of it as a processor, as a way of storing information from the past to the future. What's not in the memory, you do not store. Right? So it processes, it chooses an action, and this action together with the old world state gets a new world state. And so on, and so on, and so on. And a few remarks on this perception action loop. It is really an interesting structure. You see it's completely symmetric with respect of memory and world. Even if you, mirror it over this axis, W becomes an M and M becomes a W. So it's really symmetric. And this was intentional. We actually changed the letters we used for that. We originally had a different letter here, and we changed it so that it will be symmetric. And this symmetry looks like an idle game, but actually it's not, because if I show you this diagram and don't tell you which is the world and which is the agent, you actually don't know. So how do you distinguish something is the world and something is the inner life of the agent? And that is a very interesting question. I won't discuss it in my talk. But it's a very deep question, very deep question. So the question is, what do you consider the agent and what do you consider the outer physical world? And that has very deep implications. There's another asymmetry, and that's time. If you forget the arrows for a second, essentially, time direction is not fixed. It looks the same way, right? Of course, there are arrows, so there is a time, but in a reversible system, it's not that obvious anyway. So there are two almost symmetries here, which are an interesting thing to consider. So this is a formal property, but I'm not using this formal property at this stage. At this stage, I'm throwing away the memory because we have our little agent moving around through the world. And this agent in the world has this little reactive loop. So we threw out the memory. There is only reactive. There are only reactive behaviors. There's no memory. The agent will only pick up what it's in the state it is in and react according to that. So we have now the reduced loop. A sensor picks up something, namely where is the gradient the highest, then I do an action and get a new world state depending on where I was before and what I'm doing. Good. Now when I do that, remember what happens. This little agent starts out in the world somewhere, say in a square that has the size 11 times 11. So there are 121 states in which it could have started. At the end of the run, it's in the middle, more or less. It wobbles around intentionally. I did that intentionally, so it's not always in the middle, but it wobbles around. So it reduced from 11 times 11, that's 121 positions. How many bits are 121 positions? How many bits is that? 7. Yes, 7 bits, roughly. 7 bits are reduced to almost 0 bits, which means that this agent has processed 7 bits. Oh, well, let's find out whether it actually did it. Well, you take an agent and let it run randomly, you see that it doesn't converge anywhere, right? So it spreads out everywhere, so it's very clear that the agent has done something. It has done something. It has reduced this information, which otherwise would not have been reduced. So the agent has processed something. So these 7 bits must have been processed by the agent. It means that, that this processing has happened through this loop here. So let's have a look at this. It turns out that you can show that when you look at how much information the agent takes in over time through the sensors, so S, T minus 3, T minus 2, T minus 1, T, T plus 1, and so on, over time, you get a series of observations, and these, you can ask how much did they capture about the original state in the world. And it turns out that if you look at that information about how much did your series of sensors observations pick up about the world, this is exactly the entropy, the uncertainty that the agent had about its position in the world. This is a must. Otherwise, the agent cannot get to the center. If you make this artificially lower, the agent will wobble around in a much more bigger uncertainty level. Okay? This is, again, a cognitive invariant. So this is an equality. It's not an inequality, it's an equality. You have to have this value. So observation, again, I take the thermodynamic analogy. There is no perpetuum mobile of the third kind. Well, the first kind, the perpetuum mobile of the first kind is a machine that generates work out of nothing. It's of course impossible because energy cannot be generated out of nothing. We know that. Perpetuum mobile of the second kind is a machine that basically creates, sorry, I went too fast, too quick. Of second kind would be a machine that basically reduces entropy out of nothing. So basically, you send a probe to Venus, and it uses the kinetic energy of the hot atmosphere of Venus to create work. That doesn't work either. If you want to create work, you need to have difference, temperature difference, or some kind of difference of entropies. You need a free energy, it's called in physics. You need some way, something to produce the energy from. You can't extract energy just from fast molecules of a gas. You cannot do that. Yeah, so you need that. This is second kind thermodynamic law. But the third kind says, well, you cannot reduce entropy without taking in information that allows you to do so. Well, and that's a little comment I have below it. Actually, there may be no free lunch, but sometimes there's free beer. So sometimes, actually, you can be helped. And who's helping you? Well, I'll give you a teaser. The embodiment. The embodiment is your friend. Okay? So embodiment is our partner in crime when it comes to get free beer. Let's find out in a bit. It will come very soon. Let me just summarize what we have found. We have an information balance sheet. You have information. Information is like a bank account. You cannot arbitrarily work with it. We pretend in cognition that you can do all kinds of stuff. We have just seen with Ashby, Touchet and Lloyd, and these theorems that it's not possible always. You can't. Not everything is possible. To do certain things, you need information. To be able to squeeze out entropy, you need information. To make decisions, you need information. You don't get this information, you can't do these things. So this is an information balance sheet. In our example, the entropy of the starting state determines how much information at least you need to get to the center. Not enough information, you don't get there. Right. However, this information can be spread differently over time, or environment and agents. So for example, if I tell one of my students, can you remind me next week to that we have this meeting about that and that, I'm actually offloading information. My students have to remember, but I don't. Okay? That's possible. We can do that. Don't grin. he's grinning. Well, I didn't actually say that this time. I have actually calendar and it works. But sometimes I don't have it with me. Sensors and memory doesn't have to be the environment. It can be your own sensor or your own memory. And the invariance is purely entropic. It is indifferent to the task. So let me just give you an example for spread out or concentrated information. So let's assume, I'll take this door here. I want to go to this door. So to get through this door, this is my goal. I need to know where I am, right? If I'm here, I have a different route than if I'm here or here or here or here. There are different I need to know where I am. And now I can take exactly where I am, close my eyes, and then start walking to the door. I won't do that because health and safety regulations will probably not permit me to actually run this experiment. But I can pick up the precise bits I have to resolve to get through that door and then run it. Assuming there's no noise in the environment. Let's make it easy. However, there are different ways of doing that. I have to resolve, I don't know, whatever, 5 or 6 bits to do that. I could also do the following thing. I could say, oh, where's the door? It's roughly there. Well, let's move. Oh, it's there. It's there. It's there. It's there. So I'm basically not taking in all the 7 bits of information at once. Every step I'm doing, I'm taking a bit of information. The door is roughly there, and I don't have to pay so much attention. And then, of course, I will be going through the door with much less bandwidth. I need much less bandwidth. But the thing is, the total amount of information that I need to go through that door has not changed. That's the minimum information I need. I still need my 7 bits of information processed, except that in one case I process them at once, in the other case I process them as I'm going. This is very important. So the total amount is a minimum, but the bandwidth is not. You can have, for example, Google Maps with you, and then you look at Google Maps all the time to what do I do next, what I do next, or you look at Google Maps and at home, remember everything, and then you have to remember everything in your memory. But the total amount is still the same. Okay?
But it will be a maximum then, not a minimum, right?
No, it's a minimum amount because you can be wasteful.
Okay.
You can be wasteful, but you cannot undercut this number. Right, so we are now going to a specific task. Until now we talked about entropy only. We're going through specific tasks. I will now use reinforcement learning as a basis to formulate a task. How do you formulate a task? It's basically reinforcement learning. And now I won't explain exactly how that works. If you don't know it, you can look it up. I will just explain what you absolutely need to know. So I'm going to replace whatever we had, the gradient follower, by some general policy that takes a state in the world and now basically collapse. Of course, that's always what happens. I need this for the watch, otherwise I would have turned it off. To basically collapse the world and the sensor in one object. So world and sensor are identical. And I have the state of the world. I have a policy that the action essentially picks up. So the action decides, given the state in the world, what to do. I'm ending up in the next state, next action, next state, next action, and so on. Okay? When I do that, I collect rewards and I average them given the state. So this is the reward, the value of the current state under this policy. The policy can change. Different policies give me different values for the given state. And this is the famous Bellman formula, which allows you to actually compute it. But never mind about that. It's just here for completion. The important thing is you do stuff, you get a reward. And now the point is what reinforcement learners do. They try to maximize this value for each state. You start in a state, you want the policy that gives you the highest value. That's all. You're a little dwarf in a mine, and you have to collect gold coins as you go. You want to collect the maximum of gold coins. Right, so in standard MDP, you basically want to find the best policy. That's pretty standard, pi star. You can read it up anywhere. However, we're now going to enhance the game, make it more challenging. And in normal reinforcement learning, you do not consider the decision cost. So I could tell you, for example, how to get you're in London, and I say how to get to whatever, some place. I say, yeah, I could go this road to the left, this one to the right, then you take the whatever lane, the Fetters lane and Farnham Road, and you go and you say, I don't understand, can you make it simple? I say, yeah, you just take the subway and one station, and then you have to go 500 meters, but it's a longer route. I say, it doesn't matter, it's easier. Okay? So the cost of the length of the route may be not as bad for you as the cost of mentally having to process all this stuff. That is informational cost. And so we will include how expensive is it to process the policy. So we are going to trade off information processing with task payoff. And we include information cost and expand to the IMDP. So MDP is the Markovian decision process. That's what you find in standard literature. And the I stands, of course, for International Monetary Fund. No, just kidding. Information. Okay? So we are going to minimize information that our action needs to know about the current state. We call that the relevant information at a given utility level. So this is how we do it technically. Again, I'm not going to go into details. If you're interested, you can ask me later. But essentially, the way you do that is you remove the constraint and instead optimize the information minimization minus a Lagrangian. So this is Lagrange term. This is your average cost or your average utility in our case of your policy times beta. And by beta, you determine how important it is to you to be optimal or not optimal. So if beta is very high, for example, beta goes to infinity, means this is really important to you. So you first of all, you optimize your value before you start optimizing your information. So if beta is infinity, it means you look only at optimal policies, and amongst the optimal policies, you minimize information. There may be no other policy that the one policy that's optimal, in which case there's nothing to optimize. You have just the one optimal policy. There are multiple optimal policies. We'll pick the best one. Now, if beta goes to 0, it's the opposite. So this I becomes essentially 0. You basically don't look at your state. You become open loop. You become blind. But on the other hand, amongst the open loop ones, you still pick the best ones. So you essentially, that's a solution to the Touchette optimal open loop controller. So, and in between, you get different beta. So if you increase the value you want, you need more information. Okay, this is fun, but let's show that you can do more than that, and that's going to be even more interesting. So let's have a look at a little scenario. So I have a little grid world, and in this grid world, there are walls. So I have walls around this world. You see this, these are the walls. I start somewhere, I can go north, east, south, west. And I will introduce two goals. One is B and one is A. B is in the center of the plaza. Whatever is Ramblas, that's Ramblas, and A is the corner of the plaza. So assuming you have dropped your wallet. Well, in this Ramblas, that's not a problem because then it will be gone in a second. But assuming you drop the wallet, and for once we assume that the wallet is there, but you don't know where it is and you have to find it. Now the question is, how difficult is it to find it? Now it turns out that in B, of course, the distance to B on average from any point you start in, if you average over the starting points, is 5.5 steps. So in 5.5 steps on average, you'll get to B. If it's an A, it's longer. It's 10.5 steps. So we will give a reward of -1 because we count rewards positively. So -1 is a penalty. You want to make that path short. You want a low penalty. So A is harder, takes longer to get to. However, well, let's show you the curves first. So let's look at this point here. This is the point of optimal performance. So if this is A, there is 10 minus 10.5, so it's 10.5 steps for the optimal performance to get to A, to the corner. If I want to the center, it's 5.5 steps, so it's minus 5.5. These are the points. But if we look at the x-axis, this is the relevant information you need. It turns out that the guy in the center, the wallet in the center, takes us much more information to find. I'll explain to you in a second why. On the boundary, however, it's very easy. You see only 0.2 bits. So let's find out why that is so difficult to find in the center. Assuming it's a huge plaza, and assuming you can't actually see the wallet before you are there. So finding it means you have to have some navigational system that tells you the coordinate of this wallet is this and this, and you have to really hit that coordinate, more or less. While in the corner, it's very simple. All you do is saying, if I'm somewhere not seeing the walls, I just walk randomly up or right. Randomly up or right, doesn't matter. I hit the wall, this one, I move to that direction. I hit that wall, I move up. Very simple processing rule, requires very little information, or much less information. We see that here, 0.2 steps per, bits per step. Right. Now, I'm going to do that with a twist. Nasty experiment. Very nasty. I'm very proud of that. It's a very, very simple change, but very, very nasty. Same grid world, forget B. It's gone, right? It was the last Rumblers. People picked up the wallet before you could say Jack Robinson. The cost is as before. I'm going to now permute the directions north, east, south, and west at every spot. Every single spot has a different compass rose. Okay? Every single spot. You don't believe that exists? Yes, look at your video recorder at home. Every single menu has a different convention, right? This is what it is, okay? So I'm not changing during the game, I'm changing it before the game. Before the game, I decide north, east, south, and west mean different things at different locations. I can do that, and in fact, we submitted that to a machine learning conference, and they say, oh, well, this is equivalent, you just permute them back. Yeah, but what they did not get is that well, of course, as a traditional MDP, it's completely equivalent. I won't say I did nothing new. It's exactly the same thing. Well, yes, as an MDP it is. But as an IMDP, it isn't. So this is how it looks. Our little curves, we see the curve again. This is our old friend from before. This is A. We explained this is the best thing that A can do, optimal strategy. This is, I didn't explain the other side. I should say that. If you make a blind, it gets worse, so you can make an open loop controller. What does an open loop agent do in this world? So I will demonstrate that. So assume my wallet is in the corner. So an open loop agent is blind or drunk or whatever you want. So it will just randomly walk this, wobble here at the wall, it will wobble north, it doesn't do anything, but wobble to the right until it's in the corner. So the wall acts like a funnel. This is your embodiment. Your embodiment, the wall, helps you finding the goal. And that's why you still get 14.5 steps until getting to A, even in the open loop case for our poor drunk agent. Now we take the twisted world. Same goal, A. It's in the corner. The world is twisted, however, and we see that our sanity check, so the best policy, actually achieves exactly minus 10.5, which is exactly what we expect. It should not change the value. But what it changes is, if you look at this here, it changes the information processed. It's much, much harder to process this information. I'll explain to you in a second why, but let's have a look at the blind agent. Goes down and becomes as bad as for a random search agent. Why is that? The reason is that the blind agent here with the good directions, with the directions where north and east are consistent, basically can always do these two. But for this agent, the problem is when it's blind, basically north and east sometimes is this, sometimes this, sometimes this, sometimes this. It's no better than random search. It looks like random search. Okay? So in other words, embodiment matters. And what I mean by embodiment is something very specific. It's the encoding on what you think you're doing and what effect it has on the world in a consistent way. There's a very clear definition of what embodiment means and why you want a good embodiment. Good embodiment means you have the right codes for your actions that are consistent with the way the world looks. The fact that if I do this and this and this and this again, I get a consistent behavior is not random. It is something that the physics provides us. The world is nice to us to some extent. Otherwise, we would have a much harder time of doing cognition. If we hadn't had this consistency of space and time and many things, we would not be able to do cognition. This is one issue of embodiment. Even this small experiment, really almost trivial experiment, shows it already. So what I want to convince you of is that we see immediately the effect of embodiment on the information processing here. Immediately. Okay. So we found out what it does, and we see that an agent that can take its actions with it, so north and east mean the same thing at every spot in the world, that is an agent that takes its own coordinate system with it. It's not perfect, right? If you start drifting, it's not perfect, but it's more or less working. It's more or less consistent. And this is a kind of symmetry. An agent creates a symmetry in the world if it's well embodied. If it's not well embodied, it doesn't. So if every menu has a different type of usage, it's not a good symmetric system. And if you have to realign it at each step, your brain has to work much harder. So it's much harder to get to a high cognitive level. You spend much more resources on having it to align it. So in other words, embodiment allows you to offload informational effort. And this is essentially a quantitative way of basically formulating what, for example, Rolf Pfeiffer and his school, and in principle Rodney Brooks and all this embodied cognition school has been arguing. We argue that you can see it directly in terms of information. So I will mention a few further applications. I mentioned embodiment, which was very important. A little bit of goal-relevant information. I don't have too much time for that, but just to give you an idea what you can do with it. So we are going to look at now the following problem. We have an agent, and this agent now has not just one goal that it has to perform. It has multiple goals. So multiple goals is I going here or going here or going here, and I change these goals randomly. But I fix them at the beginning of the run. So I have one run, and in the beginning of the run, the goal is fixed, and then you run the agent. And for this, I'm changing the perception action loop. So this is the perception action loop. And I have a goal, and this goal is universal. It doesn't change during the run. So that's a random variable which is chosen at the beginning of the run. And my actions depend not only on my state, of course, but also on my goal. Before that, it was implicitly there, but we never mentioned it because it didn't change. Okay, so it was just one goal, so we didn't have to actually mention it. But now we mention it because you choose the goal, and then you run the agent. And now we're going to minimize the goal-relevant information, which means I want the actions to know as little about the goal as possible given a state. I'm in a state, and essentially I want to be indifferent to the goal as much as possible. Why is that? Well, many reasons. One reason is that our working memory is very small. With very small, I mean 2.5 bits. It's not large. Okay? This is our working memory. It can be measured. Really small. It's incredibly small. It's basically your core decision-making process. So it is a plausible assumption to say that I want to do my actions with having to know as little as possible what I want to do, as I can afford to. Again, we minimize this Lagrangian. I'm just putting it here so that you have something for reference. And this is how the goal-relevant information itself looks at different locations in the world. So the goals are randomly distributed over this maze. So these are the walls. The lined cells are walls, and the other part is where you have high goal-relevant information. You see in these corners, you have very little, because when you're in this corner, your chances are that you have to go out anyway. So in most of the cases, by default, you leave So when you have a default action, it's white. When you have no default, it's dark. So dark means you have to pay attention to what you're doing. Yeah, you have to know, do I go down, do I go to the left? Here you have to pay attention. In some locations you have to pay less attention. Some locations you have to pay a lot of attention, say these crossroad. But this is not so exciting. Where it gets exciting is here. Here we look at subgoals. Now people model subgoals in machine learning by saying where do the agents pass through, what are the most visited places, blah, 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 all these things. We decided we don't like that because this is handcrafted. I don't know where subgoals come from, but I'm claiming that subgoals are basically an effect, an epiphenomenon of cognition. Then they must emerge from cognitive constraints. So we argued subgoals emerge because our cognition is limited. And here we say, what's the limit? We are asking if I'm in a particular state, okay, that's what we always have because it's state dependent, of course, and I have a history. So here we encoded the history as a series of actions, but it could be the whole history, everything you observe. Here it's deterministic, so the series of actions, and the current state determines everything. So that's why we can write it this way. So consider this just as a complete history. And now I'm saying, I'm now making let's assume this is a door here, and I'm now making a step through the door. While I'm on the way out, I'm going out of this building, I know the first thing I need to know is just I need to go through this door. I don't need to know anything else. If I say I want to go Sagrada Familia to the 3rd level and looking out to the city, it's a very complicated route. But if I'm in this building, the first thing I have to do is going through this door. Nothing else. When I leave the door, what do you do usually when you leave a building? You look around. Well, why do you look around? To orient yourself, and perhaps also to do a cache fetch. What's the next subgoal I need? And this is what you see here. You can ask essentially, given a history I did, what's the next information about the goal I need for my next action? And this is how much I can forget about the past. And let's have a look how these things look. So here we see that they are high when you cross the door. And by the way, this is not symmetrical. This is high when you go from the left to the right. This is high when you go from the right to the left. And these are subgoals that emerge, but you notice here something else. If you do this formalism, you discover other subgoals, and these are interesting spots at the center. Well, here is this, but here, and here, and here, and here, at the center of rooms. So at the center of rooms, there are subgoals you don't normally identify. These are spots where you have to, do I go here or here? Yeah, I'm going here, and now I have to decide, do we go through this door, this, or that passage? This is a decision I'm making in the middle of the room. It's when I have to realign myself to the actual external goal. I have to take in new information about the goal I'm currently pursuing. Think of it as a long-term goal being the thing that's expensive to store, slow to process. The current goal, the sub-goal, is what I process for my actions, what I really use for my actions. You see that immediately here. The discarded goal information, you see that it's mostly discarded in the doors. And in fact, we found this result in 2011, actually. At that time, there was actually paper that showed that psychologically, when you cross doors, you tend to forget stuff. Yeah? What do I want here? You cross a door, you forget stuff. It really happens, okay? So this is possibly a reason why that happens. You just basically clump together your knowledge, what you need, and then you forget stuff, and you forget a bit too much, okay? Yeah, because it's not so easy to separate these things. I want just to, well, I'll skip that one because I want to go to empowerment in the last phase of my talk. So empowerment is something that we are going to look at in terms of why an organism knows what to do in every situation. And it's not always the case, but it's surprisingly common. So let me come from biology again. Again, I'm talking about biology. I had a meeting with a good friend of mine, and it turned out that he was a creationist. right? I mean, it's a bit like finding out that somebody supports some candidate which you really thought, oh, well, that is really unexpected. On the other hand, he was a very intelligent guy. And I thought you need to take every argument seriously and see whether you can defeat it properly in a scientific way, not just dismiss it because you don't like it, right? An argument needs to be defeated. But let's summarize one problem that people have, and I'll suggest a solution. Solution that works in the framework of Darwinistic thinking too. So just to make sure. So in biology, we assume the success criterion is survival. And when we talk about a task and reward, this concept is not sharp. So we set goals, but we pretended there's a goal. But in reality, that's not really the case. Of course, we have the goal to eat and so on, but this is emerged through a long process. In principle, if we would float through a feeding substrate all the time, we probably would not look for food anywhere. We don't usually look for air, right? Air is around us, so we breathe. It's only a problem if we're diving or in space or something, but normally, looking for air is not something we are doing. Breathing is not a goal, normally. Hopefully it will stay this way. Right, so this is not a sharp reward. So the question is, what is it that we're actually looking for? Also, the search space is too large for a full-fledged success feedback. Yeah, it's a really huge space. People say, oh, there are trillions of bacteria. Yes, there are trillions, but there are gazillions of possible DNAs. It's a huge space that you could actually explore. And if we say pure Darwinism, or naive Darwinism, I'd rather say, because Darwin was smarter than that, you would say feedback is given by death. And imagine that. It was like an exam. You're a student. You study and study and study. No exams, no teachers, no something. You just do your stuff. At the end comes an exam, at the very end of your studies, and the responses fail. It's not very helpful, is it? Yeah? So in other words, feedback by death is very sparse. And it's actually not very informative too. And that is a problem of naive Darwinism. Of course, people will say homeostasis provides dense networks to guide living beings, so it tells you where to go. Stay out of this, eat if your blood sugar is low, drink when you're thirsty. Yeah, there you go. And all these things. But the point is they are specific to particular organisms. Okay, not hunger and thirst, but for example, there are levels of pH that you want to reach and so on. That's very specific. If we do RoboCop, you design the homeostatic rides by case-to-case basis for artificial agents. That's really not very efficient. You have to reinvent the wheel every single species. That does not make sense. You want a more generalizable perspective. And the question is, how can you do that? Well, I give you a couple of ideas that have been merged essentially in the last decade and a half, with one exception, which actually dates back to Schmidt-Huber 91. It's quite a cool idea. Artificial curiosity, Kaplan-Udier learning process, autotelic principle by Steele's, intrinsic reward by Seng et al. And one principle that we are probably closer to, that's Ralph Daire and Nihad Ai's homeokinesis and predictive information. Finally, some guys that have basically rediscovered the principle I'm going to say in a second, in a physical context. So they call it causal entropic forcing. And it's very, very related to what I'm going to give you as our Ansatz. Our Ansatz is based on information theory, of course. Essentially what you say, I'm optimizing the informational fit into the sensory motor niche. What I'm maximizing is the potential. It's not what I'm actually doing, but the potential to inject information to the environment. So throw stuff around, move things, modify my environment, and observe that again. So if I can blow up a whole galaxy, but I can't see it, it doesn't count. Okay? So if I'm blowing up, I'm pressing a button here, right? Let's press a button here, whatever, and this blows up some faraway galaxy, you know, with Darth Vader and the Emperor Palpatine, whatever, all in one, and we don't know about that. It doesn't count. It only counts if it appears in Hollywood and they show a movie about that, but that's a different story. So you need to recapture it. So in other words, being in control of one's destiny is good. That is how Tobias Jung formulated it. I thought it's the best formulation you can have. Being in control of one's destiny and knowing it. That's why we call it empowerment. We stole the word from social science, because that's exactly what they say. You are in control of your destiny, and you are aware of that. That's very important. Both are important. Being in control and being aware of it. So, for more technically oriented people, you can consider it as a mixture of controllability and observability in terms of information theory. So let's look at it in the Bayesian network. We have our Bayesian network, and now I'm throwing out the memory. Okay? And I'm throwing out what the sensors do to the actuators. And I'm now basically choosing my action freely. I'm choosing here an action, a possible action. It's kind of, I'm projecting to the future. I'm doing something to the world. It moves on. Now I'm doing again something. It moves on. I'm doing again something. And now we're observing. So basically, it's a bit like a guy that throws stones around, and after having thrown some stones, let's say, okay, how many windows did I break? Right? That's kind of it. And basically, I'm looking at a series of actions and look at the effect of them. And now I take all the probability distribution over these three actions, and they can be joined. So I can have a memory. I didn't put it in to not confuse the picture, but essentially the three actions can be correlated. And they can also depend on the starting state. So knowing the starting state, I choose these three actions and look at the effect they have. And now I choose the distribution over these actions that maximizes this effect. Maximizes how much effect I can have on the last state. And that's how we compute it. So you maximize how much the series of actions can affect the final observation. So I'm maximizing of these. Of course, it depends on the starting state. So the starting state is WK. So it's actually a function of the starting state, given of the starting state. And I will be even more compact. I just write the series of actions as one variable. So you essentially can look at it as one blob. And when we do that, we ask for potential information flow that we can inject through the actuators into the environment and recapture later. Think of it as the informational efficiency of the sensory motor niche. How efficient can I modify my environment so that I can see that? If I can do a lot of things but I don't see it, doesn't count. I want to see what I can change. If I can't see it, I remove my sensors, I recover other sensors, or I remove my actuations and move my actions there where my sensor works. So I want them to match each other, if you like. And if you want to think of it, what could correspond to something I know about? Well, in games, for example, mobility, I want to be able to access many states in my game. Of course, the classic one is money. Yeah, having money gives me a lot of options to do in the world, and I can see what the effect is. Affordance, that's a classic of embodiment, of course. If I have a door where I can naturally pull the button there, very modern design door like POLANI or something, and then how do you open this door, right? You do stuff and you don't know how you get the effect you want. And essentially, it's antithesis to helplessness, to learned helplessness. It's the opposite to helplessness. You are helpful to yourself. You are able to modify your world. So, let me give you examples. If I'm in a maze, I can be somewhere, say for example here, and now I can say in 5 steps, how can I change my world? Changing my world means going to a particular state. How many states could I reach from here? It's potential again. It's not what I'm actually doing. It's what I could reach. So I am here, I can reach many states. If I'm here, I reach only few. Okay? So white means its empowerment is low. Black means empowerment is high. And these 4 different cells, they are only different on how far I'm looking to the future. This is 1 step, 2 step, 5 step, 10-step empowerment. You see they're quite similar actually, right? So this is empowerment is the value, the mutual information that I can get when I'm choosing a series of actions. And if you look at this one, this is a standard graph measure. It's basically the graph centrality saying how many what's my distance to every other cell in my graph. And when that distance is low, I get a dark value. When the distance is high, I get a low value. And if you look at empowerment map and this map, they look very similar, and we can compare this and this. When we do this, you find that empowerment, so the set of cells I can reach in a given time, say in 5 steps, this is this axis, and the distance, the average distance to cells, they are almost perfectly anticorrelated. They're not exactly anticorrelated, they're not exactly the same quantities, but they are very close, except that this is a measure that's specific to graphs. It doesn't work in stochastic systems. This one is completely general. It depends on the sensors. It can process randomness. If there's randomness, you will count less. Randomness reduces your empowerment. If you walk over a very wobbly surface, you will be unsure where you end up, and then your empowerment will go down, in fact. So this is one example. Another example is here. Well, this should be very interesting for people that like Barcelona football. Yeah?
Is it about how many states you can reach?
Yes.
Or how many states you can predict that you can reach?
Well, it's both. Because normally, essentially, you need a forward model. It's not what you actually do. You need a forward model. So if your forward model is bad, then essentially you will get lower empowerment. Okay. So it's a mixture.
Randomness doesn't reduce it.
Sorry?
Otherwise, randomness doesn't reduce it.
Otherwise?
If it's not about prediction, you can have randomness and still have high empowerment. If it's not about prediction.
No, the opposite. You can only lower it. If you have bad prediction, you lower the empowerment. If you have randomness, you lower the empowerment. If you have both randomness and bad prediction, you lower the empowerment even worse.
Okay. So it's about the state you can reach and predict.
Yes.
Okay.
Yes. 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 So here we have an example that's very, very interesting to Barcelona fans because it's essentially football. So think of it, this is a football in the middle, or there's a box you can't move. There's an agent that can move around. Now this football is now nailed to the ground. Okay, it's a bit like Lucy and Charlie Brown. So you can't actually kick it. So if Messi goes and kicks it, it's bad. And what happens is that the empowerment outside of the football has a certain value, is how many states you can reach in 5 steps. That's 61 states. When you come closer to the ball is an obstacle. Because you can't move it, it's an obstacle. And then the empowerment goes down. You see that it gets white. White means low empowerment because it stands in the way. You can't move as fast and as freely as you would like to. Empowerment goes down. If you stand on the ball, of course, you can jump down and then you have maximum empowerment. That's why it's black on the ball. This is for the case when the ball is nailed to the ground. Here, the ball is not nailed to the ground, but you can't see it. In this case, empowerment is equal everywhere. And the interesting case, let's forget this one. The interesting case is here. Here you see white is again low empowerment, but low empowerment is the same here as black. It's the same value. When the ball is in the center of the room and you can move it and you can see it, suddenly empowerment goes up by 2 bits almost. So I will soon finish it in 5 minutes. When I'm getting to the ball, the empowerment goes up. So I can manipulate not just myself, it's my own empowerment, my own movement. I can also manipulate this object in the center. So you see a whole bubble of empowerment. See, basically, here, without telling the system that it should go to the ball, like having a messy robot, I don't tell the robot, this is a ball, you should go to it. It will discover on its own, by virtue that it has more manipulability, more potential in the future, that it should go to this location. So I have here an example of how you can move through these steps. So here we have a system where the ball is fixed to the ground. Now, when it's fixed to the ground, and then I release it. So it becomes more and more motile. This is the empowerment map. Yes, and you will see this is an empowerment map, and the empowerment map changes as I make the ball more and more flexible. When I make more flexible, you see suddenly that the empowerment goes up. As the ball becomes more reliably movable, empowerment grows, and it becomes more and more attractive to go to the ball. As the more reliably I can move the ball, the higher the empowerment becomes. So when I perfectly can move the ball, the empowerment has almost these 2 bits. So this is a little example for empowerment, the taxi domain I could skip. I'll show instead something else. This is a pendulum. Essentially, this shows the angle and this the angular velocity of the pendulum. This is a pendulum that swings up, and turns out, okay. Yeah, it's just okay. It's okay. It's just and you have a pendulum and it swings up. And it balances on its own, basically driven by empowerment. You don't tell it to put it up. You just say maximize empowerment of this pendulum. Now, the cool thing about this example is that here it's learning the map on the fly. So instead of reinforcement learning, where you have to learn the whole value map, you don't do that here. You learn only the map on the spots where it actually visits, which are locally driven by the local empowerment gradient. So it's purely greedy and local on empowerment. And nevertheless, it learns the map almost in one shot. Of course, this is again an indicator that pendulums are actually an easy task if you do them right, if you use the right embodiment. So it's not generic problems that can be solved this way. It's only worked for things that are actually quite natural. But humans are pretty good at that. But machines seem to be very bad because they don't use the embodiment. Again, empowerment requires embodiment because you require actuator and you require sensors. And here I have another example. This is a two-link pendulum, which is a difficult task in reinforcement learning. And it's extremely difficult, so people usually break it off when it gets above a certain limit. This is driven by empowerment. Again, no external value function except for the end, where we added in one action. Well, we didn't add the action. It was just in the toolbox of the agent for the very last part. We saw it tried to get up there, and close to the top, it couldn't balance it because it is a bang-bang controller. It's a really primitive controller. But at the top, it couldn't do it. So what Tobias had, it added one action to the toolbox, which was an LQR control. LQR control does not work on the most of the pendulum. It only works close to the top. And usually, all the papers, they start to turn it on actively. They basically have some threshold and say, turn it on now. We didn't do that. We just added it to the actions, and it chose it when it wanted. So basically, empowerment chose the thing to do. This is another example. This is Pac-Man, again, driven by empowerment. Pac-Man has to survive. Empowerment is a survival, essentially a survival algorithm. And you see yellow is Pac-Man. The three ghosts are pretty aggressive. They're actually all of the strongest ghost type. So this is not the pure Pac-Man. And you see that Pac-Man is pulling the ghost behind him. And you think, oh, this is really dangerous. It is. But the idea is that if he controls the ghost empowerment, right, he manipulates the ghosts, he knows where they are. He makes them go where he wants them to go. Okay? This only works because empowerment is a control. Well, they caught him at the end. But it really is performing much better than, say, a moderately trained human.
What is motivating the agents here is that if it is caught, it dies, and then there is no
empowerment.
variety.
Yes, empowerment is a survival skill. So basically, empowerment, it's zero when you die. And therefore, you want always to stay away from zero. And this is another example for really a big collective system where every agent observes the density of other agents around himself, just around himself, evaluates its empowerment. What happens if I go there? What happens if I go there? And empowerment is maximal if you don't want to be at the center of a blob because you can't move there. You don't want to be alone because then you don't see anything because there's no empowerment. So you want to be basically in interesting spots like at the edge. And so you get a nice critical behavior where you are always in the tension between moving close to others and not being trapped. And this is kind of a nice example for a collective empowerment model. And I think this is the right spot to conclude my introduction into information theory and embodiment. Thank you very much.
Well, thank you very much, Daniel. It's a great talk. Okay, do we have questions? Please.
Yeah, my question would be, but it still wants to be sort of universal, right? Universal criteria, but the dimensions that are relevant to empowerment, they are still selected arbitrarily, are they not?
No, you have to say what's your actuator and your sensor. Right? You have to say that at some point, but you can evolve that. In fact, we have an example for evolution. I won't go into details, but we have actually a case where we evolve the sensors. So you can basically do stuff, it can be even random, and now you evolve the sensors to increase empowerment under the actuators you have. Or you can fix the sensors and evolve the actuators, or it can evolve both and maximize empowerment. So really, that is not...
But within a very complex sensor space?
Yeah.
Thinking of humans, how do they pick what's relevant for their empowerment?
Well, you can do a greedy search. The cool thing seems to be that if you use information theory as a guiding principle, then you essentially end up with a relatively benign search landscape. Why this is the case, we don't know, right? There's not a mathematical law. That's not a mathematical law, but the landscape seems to be much more benign than for many other fitness functions. Yes.
So in your empowerment model, you assume that the forward model is already learned, right? Or is given to the agent.
It can be learned on the fly.
It can be learned on the fly as well.
Yes.
Because my question was, you mentioned some, let's say, artificial curiosity framework, like Schmidt-Huber for, I think it's the compression progress idea of Schmidt-Huber, or the learning progress idea of Udeye. Yeah. So they are based on the notion of progress, so of learning.
Yes.
So they are exploration strategies as your model, but the only, I mean, one of the main purpose of exploration strategy is learning. So yeah, my question was, have you tried to apply your method with a forward model which is learned online?
That was the Pendulum. The Pendulum was one.
It was learned online, this one?
Yes.
Okay.
That was the whole point of that experiment.
Okay, and then do you observe similar effects than in Schmidt-Huber or Udeye framework, like developmental sequences that can emerge from these exploration strategies?
We think that it's orthogonal to them. So if we compare Schmidt-Huber, I would rather compare it with predictive information and Nihat I and Ralph Dare's homeokinesis, because they are process quantities, while empowerment is a state quantity. So empowerment, my students had actually a fantastic picture for that. They say the homeokinesis model is a bit like a baby, tries out stuff and sees what works, blah, 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 whatever. And empowerment is essentially when it's learned. After learning, it's a bit like the wise man on the hill. He knows, doesn't have to do, right? So the model is here, empowerment ends up in a state of where it understands what it can affect on the world. It's not interested in running the process necessarily unless there's a reason to do so. Okay. Right? But of course you're completely right. I mean, if you want to learn, you can use empowerment to learn. And this is a relatively unexplored area. So we have not done much on learning and empowerment. Intentionally so, because we think learning is very complicated. And we want first to understand, is there a way of having a universal value function for organisms? Because if there is, it means it's much easier to become a clever organism than it looks to a creationist.
So thank you for the great talk. I wanted to ask you, you assume like a fully observable words, right? So
depends on the model, not
okay.
everywhere.
So, but would it work also like on partially observable words?
Empowerment is partially
okay.
observable.
Okay, so
empowerment is specifically for I always emphasize the sensors matter. Right? If your sensors are very limited, your empowerment landscape will be looking different, of course.
okay.
Yeah. For example, what I didn't mention here, I pretended empowerment is computed for a particular starting state in the world, but of course you can make a subjective starting state. We call that the context. So empowerment can be context dependent. Okay. Yeah. And everything else could be made for a POMDPs, but we were not primarily interested in saying solving POMDP learning problems because many people do that. What we were interested in establishing, are there universal properties of embodied loops which we can use to drive our learning rather than imposing reward functions. One problem is that where do you get your reward function from? You can choose this or that, and there are many that are equivalent. There's not rewards are a problematic concept in terms of evolution and artificial life.
Just a short question is, you mentioned that there's a feedback as death is not a good feedback, but your later theorems actually prove this very good. So, for example, if the course is life and the exam is survival, if I'm able to observe the world around me as I'm empowered, then you eating an apple and dying would give me a lot of information, a really good feedback. So embodiment would be my sensor of the world. So I'm wondering how come this theory is not good since you proved it right?
Well, okay, I did not talk about this. The concept of digested information. This is what we call digested information. So you do something, and I mentioned earlier that information is symmetric. So if I have state information about the state in my actions also inform about the state. So if I do something, and for example, I'm sitting, this is typically a situation, supermarket, the last good bananas, right? All the other bananas are already dark and already good. I don't like. I like them. More on the yellow side. Anyway, so there's the last good banana. This guy stands in front. He looks at other stuff, and you look with covetous eyes on the bananas. He sees you. He grabs the banana, of course. So you have to hide it, right? You want the bananas. You know that you want them, but you look. Oh, there are the pears and ananas and pineapples and this. And this guy looks elsewhere, moves away. Wham! Banana's yours. Don't reveal, you go. You reveal, you go when you do that. So this digested information, you're completely right. On the other hand, yes, of course, feedback by death is strong, and that's why we have averse to blood. That's why we don't like splatter movies are basically working on that. You say, oh, splatter, oh, it's dangerous, right? It's a warning to you, of course. But it's an extreme warning, and usually you don't always have somebody else that is ready to die for you so that you have this information, right? And that's also very costly learning. So feedback by death, yes, of course it's feedback, but when that happens, is really should not be. This is something that sometimes is being spent, but it's not something that you want to happen a lot. It's expensive.
Yeah, I have two silly philosophical questions to argue about during lunch. So the first one is a minor. You said one event you cannot do stats about it. 2 events is great because you have something to argue about. But you seem to know Bayesian Laplacian statistics. So you know that one event you can still define a prior and argue about the probability of that event. That's a minor. The second one is even more interesting to argue about is you seem to follow the path. You have Turing Church computability, you added information theory, and then you end up with Jaynes and the others in physics who seems to believe in the digital physics universe. So you think the universe is a cellular automata or a computer?
For number 2, I'll say something. The first one is a simple observation. I mean, of course, I'm tending rather to Bayesian view. However, still, the prior is a really complicated thing. It encodes a lot of history or a lot of prior knowledge that you pretend is somehow there. What I'm talking about is Neeman takes here, he basically talks about binning. So if I say, I see, you look at the universe and I see us as intelligent organisms evolving from the universe, just one species with that capacity, that doesn't tell us anything. How likely is it to get there? We don't know. If we say 2 species, another alien species somewhere in the galaxy that has intelligence, we have a statistics. That's what I mean. If we see one event, we don't know anything. Not if you don't have a prior. If you have a prior, of course, right, but the prior is a lot of information. So I'm not anti-prior, don't get me wrong. I'm actually working with them. But I do think when you really don't know, like in the case of life, like in the case of intelligent life, basically I would say you really don't have a prior here. And it's not well defined to talk about a prior. If I see the sun going out every day, yes, I have a pretty good prior. I can make a prior.
P of P could be a nice prior for that,
No, where does P come from?
Yeah, but you may, well, that's what people in the origin of life are doing every day, so they can compute about permutations about in the DNA or RNA space, and you think about it, and then you build a prior on that, and you get a number.
Yeah, but this is exactly the problem. Turns out that this prior is much more skewed to be successful. Must be much more skewed to be successful than it is, and we are trying to find ways of how it could be skewed, right? But we can discuss that. It's an interesting question. To the second thing, I'm absolutely not of the Church-Turing thesis. Absolutely not. In fact, I do believe that Turing actually was brilliant. It's a very, very cool idea. I just don't believe that Turing is the right way to describe our world. In fact, the opposite. The embodiment of Turing is one of the worst embodiments you can choose. Embodiment in the world is physics, and that is perhaps it can be modeled by Turing machine, but in terms of embodiment, Turing machines are really ill-chosen. And the fact that I'm using information theory doesn't say anything about how the computation looks like. I try to emphasize that the mechanism is something I do not care about.
Yes, but you still have the hypothesis of the digital universe.
No, this is a misunderstanding. People think that because we talk information theory and you can see information theory as symbols being sent over a line, then this is how it works. No, it just means it's equivalent to that. It doesn't mean it's the way it works. They are two different things, because you can have a completely analogous world. You can have a dynamical system in the real valued dynamical system and still do information theory. In fact, you can do, a symbolic dynamics is a way of turning a continuous analog dynamical system into something symbolic, but doesn't mean that's how it works under the hood. So I'm very strongly against saying it's like this or it's like that. I have no opinion about that. I think the closest you can talk about is Schrödinger's equation or Dirac's equation or whatever field equation you have, and then you can ask, what's the information processing signature that is embodied there? Yes, that's something I'm happy to talk about, but I'm not saying it's a cell automaton. No way. In fact, I don't think it's a cell automaton.
All right, you guys have lots to talk about this. Gregor.
Quick question about the idea of embodiment. Did you try all of this on real robots? Because you said at the beginning that it was completely...
We have a bit of experiments on real robots, not much, because it's actually something we are trying to move towards. But I'll show you one experiment we have. This is it. But generally, this is a very primitive experiment. It's done on the Corvus project, a European project. Can't get it bigger. So the robot has to go to kneel, but the robot also has empowerment in it, built in. So it will not go through the two boxes because they will constrain him. So we'll try to, we'll go through to kneel, and there's a landscape, which is a combination essentially of a normal goal-directed landscape together with an empowerment landscape. And that empowerment landscape is basically constrained because the boxes, when it goes through the boxes, it could be stuck. I mean, not in reality, but it has a model of that being between the boxes, it loses degrees of freedom. So think of it as a robot on Mars, on a comet. When the robot feels that it loses control or grip over how it's moving, then it would stop and go somewhere else.
But do you think this could allow to get rid of the variability that could happen in building different robots?
This is one of the goals, yes, on long term.
For me, it might be something different of what we have. So it's still one more that is still different from the other.
Yes, the idea would be exactly that you get rid of the variability of your environment, you get rid of the having to code for every possible exception. Say you have a robot that walks and then it's slippery. So it loses control, and I would expect the robot then to take a step back, for example, because it loses control, or try out how it would get control over the less grippy surface. So yes, the goal would be that you would have a machine that's, without having to code for every exception, would do these adaptations on their own.
It would be better to have several machines with the same to prove it.
Yes, in principle, yes. But putting empowerment on robots is basically hampered by numerical and filtering problems. That's why it takes time, but we are making progress. It's just much slower than it looks on paper. On paper, things look much easier.
Hi, great talk, thank you. One thing that wasn't really clear for me is, so let's say that the motivation of an organism in that case is empowerment or maximize empowerment in a way.
Yeah.
So if you have, well, okay, I think we will talk about this over.
It's a long question, or?
Yeah.
Okay.
Hi, yeah, thank you for the talk, very nice. But I still have some things that are unclear. For instance, in this example, did you say that you've explicitly coded the fact that the robot shouldn't go through the boxes?
No, we coded model. What you need for empowerment is a model what will happen when you do certain things. So you have to have a forward model. And here the model actually tells it how many degrees of freedom it has, and the model tells it that it can't move the boxes, which is not correct. Of course, it could move it, because they are just cardboard, but the internal model says you can't move the boxes. It's like I'm telling you, this is a very heavy thing. So if I tell you this is made out of osmium, I would, and then I would find out it's not true, right? But you would at first think this is an obstacle, okay? So empowerment lives from a model. And if the model is wrong, your empowerment estimate is wrong too, but that's fine. Empowerment is a purely subjective quantity.
But you can also estimate the model, I mean, without any knowledge of the environment?
Yeah. You can of course make adaptations. For example, the pendulum, that's what we did.
Because I was thinking an agent that has no knowledge of how the environment works, maybe you need a long sequence of actions in order to actually have an effect on the environment. And originally, if you don't know this sequence, you might not end up anywhere, right?
And as a human, you have the same problem. If I give you a computer game and you press all buttons, nothing happens. Yeah, and you know, Paul knows that after the 100th press, something will happen. But you have no idea. You press, you stop after 20 presses, you throw it away. So in other words, if you don't see that there's an effect, you do something that has an effect.
So you just do random actions until something happens, basically?
Yes, and that's what babies actually start doing. And if you deprive babies of that experience, that's not good for them. Even as humans, I mean, I mentioned helplessness. There's an experiment with dogs, a very nasty one. They took dogs, gave them electric shocks, and then the dog was thrashing around, and there was a lever. When they pressed the lever, the electric shock stopped. Good. Then they took another group of dogs, again, same experiment, electric shocks. They pressed the lever, nothing happened, and they got electric shock further. So they changed rooms. They put them in a different room. In that room, there were two boxes. One was electrified, the other one was not. The first group of dogs that discovered that pressing the lever helps them to escape the electrification jumped to the other room and were saved. The second group of dogs who learned that pressing the lever would not help them, they didn't do anything. They just laid down and whimpered. This is called learned helplessness. And empowerment is about learning that, yes, you can change the world, and you discover that you can change it. If you don't know that you can change it, it doesn't count. It's very important. It's very subjective.
Thank you very much. It's a fantastic talk. So you mentioned Ashby, and you talked a little bit about homeostasis, and there's a lot of other cybernetic principles, sort of perceptual control theory, and so on. Is the goal to kind of unify some of these concepts with this theory?
Yes.
So now if you go back and you want to, can you explain homeostasis as a particular way of taking this theory with some constrained way, and that would give rise to homeostatic systems?
Well, homeostasis is a very special case of a general principle. So homeostasis requires you to get to particular states, to remove entropy from the environment. And we talked about how that can already captured partly by what we know. Of course, when you have a particular goal that moves around, then we end up in an MDP, so it's a generalized version of homeostasis. And there is now a series of papers that look at how much information how much information you need to achieve a certain goal, or how much information you need to control a control system. So I think we're moving towards something that could be considered a wider picture of the whole story. However, of course, homeostasis is not the whole story, because a living organism is not in a static state, usually. Most of the things are drifting or moving or changing all the time. So the question is, what is the right balance of movement and dynamics that you want? And that probably is better answered by something like homeokinesis, which is an extension. So you want to move into states which are precarious, but you still have control over. That's the Ralph Dare's theory, essentially. Ralph Dare and Nihat Eyes. So predictive information maximization, or learning progress. I personally think that learning progress is already higher level. It's something that is already a meta level, is further up on the scale of complexity. So I think a simple organism doesn't care about learning progress. A simple organism cares about being able to be a living precarious environment and control it, rather than becoming, the next Einstein E. coli bacterium. I think that's more human. So humans actually, by development of their prefrontal core, basically the planning area of the brain, have this additional component of wanting to learn and compress knowledge, because they found that this actually improves their survivability. So I think it's meta phenomenon.
But I guess it relates to what you were talking about earlier about the cost of all this information processing. So there's a cost to the empowerment.
Yes. I did not combine them at all. Thanks for observing that. I said it's cost of processing information, and I said I want to maximize my influence in the world. And I did not say a single word about what happens if I say, oh yes, empowerment, yes, but not at any cost. I didn't talk about that. There are ways of reducing it, and in fact it gives rise to what we would call dominant strategies. I don't know whether I have slides about that, but you get, no, I don't have them here. You get basically dominant strategies. So say things that I want to remember. For example, you play a game which you're not playing very often. You play a game once a year, you play some game. So you don't want to remember every refined stuff. You know the main important things. Try to remember some main strategies, and that's what you do. So the idea is here, and we get that also as a result, that you keep some main arteries of strategies, and the rest you throw away. And that actually comes up. So if you're interested in that, I can point you to some papers. But it's a very good question, and we have just scratched the surface. It's not combined. Empowerment doesn't care about the cost at this stage. The when version of empowerment I told you about. But if you start caring about the cost, you get main strategies, something like that.
My name is Gerçek. I study economics and neuroscience at the same time. And as someone who has no computational background, I still was able to follow your seminar, so thank you.
Most welcome.
Yeah, I'm a social scientist basically, so I want to learn about how this implies to, you see, I see cognitive decision making under risk and uncertainty. But this uncertainty is not just the Knightian uncertainty in the classic sense, because there's your reward, your outcome depends not only on your own actions, but the actions of the other agents. And humans, they are not rational, they are basically stupid. And they don't, okay, let's take a similar setting. Like in a crowd, you're in a crowded street, there are more agents, and they're humans, so they're not rational. If they were to pick the optimal roads, let's say you are not going to bump into each other, but they are stupid. And so in each step you have to calculate in their stupidity in your steps. So how does this implies how do you implement this under complex real life conditions?
Well, let's leave the complex real-life conditions out because I don't think there is any robot. I think it would be a robot challenge to have the so-called Oxford Street robot that on a Saturday afternoon can move through Oxford Street with a maximum velocity. So that would be a challenge that I think would be a real one. But we have actually something partly to answer your question. We have looked at obstacle avoidance, so by empowerment. So you have a robot, it's an agent, it's not a real robot, but that's something we would like to try on a real robot at some point. You have a robot that moves, and then there's another robot, and that other robot can have three characteristics. One is it's perfectly predictable. It goes in one way and it's exactly predictable. It will never change what it's doing. In the other case, it's slightly unpredictable. The third is completely erratic. And now imagine if it's completely predictable, what you can actually do is you go with the robot, you even bump into that and use its, its impact to move yourself into states that otherwise you wouldn't reach. If it's completely predictable. So you could do that. People do that in some cases, for example, when they bump into, I don't know, there are games where you can bump into a bound and get thrown back or get a trampoline or I have no good idea for now, but in principle you can imagine games like that. In the case when it's not exactly predictable, then it makes it difficult. Then you make a slight move around. And in the case when it's really erratic, you stay away from them. I mean, that's why you do. But why do you stay away from real humans and don't bump into them? It's very simple, because bumping into a human is read as an act of aggression. In other words, that could end really badly. Like, he beats you up or whatever, right? So the main point is, if you know that person can't act, people are actually more careless. So if they feel that somebody cannot really react, they tend to be more careless, at least in a very crowded environment. In a very polite society, there's a joint information, basically a joint rule of engagement where you have already these rules, and if you break them, actually it's called rude. If you have a queue in Britain and you jump the queue, well, people will really be angry. And this is just a social convention. But of course, you do the same thing in Italy, nobody cares. Right? So this is really convention. But if you leave that out and you say, okay, we don't care. For example, in Britain, there's a property in Germany, I haven't seen that. So somebody stands in front of the a showcase somewhere, and then they start stepping back, and you move behind them, and they start walking to your way. They just don't look where they look at. Doesn't happen in Germany, or at least when I left Germany, it didn't happen. You could move behind people, and they would never step back without looking, never. In Britain, they do that all the time. So I had to learn that the hard way, that essentially British people are essentially omnidirectional. Germans are not. Right? Germans will usually walk in the direction they look. Okay? So
we can test that.
This is an experiment that actually could be tested, and I found that very striking. You cannot predict where a British person will move to, in which direction. And when you know that you have to factor that in your movement. So yes, I completely agree. This is part of the model. If your model is wrong, you will bump into them, and will have to learn the hard way.
So to finish up, a very fundamental assumption behind your whole analysis is that information processing is costly.
Yes.
Right. And that then translates to a notion of entropy. So that basically means, in physical terms, you want to minimize the variability in your information processor.
Mm-hmm.
Right?
Yeah.
But now, this is an important question. Is that really true? So, if you look at brain structures that implement this kind of information processing, like your cerebellum, you would have, let's say, baseline activity of 100 hertz across your Purkinje cells, which is extremely costly. And this is 60% of your, this is a central point in brain circuits that cover about 60% of your neural volume. So I really challenge this assumption. I don't believe that at the level of the variability in the physical system, that is the optimization problem. I think the optimization problem there is much more to do with latency of your actions in the real world. And this goes then also a little bit back to Tony's question earlier, right? That on the one hand you want to optimize information, but on the other hand you have to deal with your empowerment, which means physical action in the real world. And this also then cuts across to the implications for embodiment. Because, okay, embodiment gives you information, right? Okay, but then in informational terms, what's the information gained by virtue of being embodied? That would also mean that morphology of embodiment would have a quantifiable impact on your information processing.
Exactly.
And you didn't really express that too clearly, right? So I think, so on the one hand, I really want to challenge you, but maybe this is a much broader discussion than for now. We can also have it over a number of beers and dinners. But so question one is, I feel we should really inspect this fundamental assumption about information processing is costly with respect to variability in a physical system. I'm not sure that's the case. And secondly, I think we then have to really see what's the information gain of the embodiment in quantifiable terms, because that's not so obvious, right?
Well, the information gain, I mean, the experiment with a twisted world, that idea of that was trying to move towards that.
Yeah, exactly. Okay.
So that's partly an answer. The second thing is, you're completely right. There are two contradictory drives. One is empowerment maximization, which increases information processing requirements. One is you want, however, to be lazy. Think of it as an economy. An economy expands, but essentially you don't want to spend a lot of money, right? So you have always this balance between investment, which is long-term, and expenditure, which is short-term. So I think it's a matter of timescales rather than saying, I mean, the contradiction is if they pretend that they happen at the same time scale, but they don't.
Right. Though if you look at latency,
yes.
Why is your cerebellum at this incredibly metabolically demanding firing rate continuously? Because it wants to control latency of its outputs.
I agree.
Okay. So this is then another optimization criteria.
Latency, in fact, has a lot to do with information because
or action in the real world.
Exactly.
Right.
Yeah, if you want action, fast action, you mean you have to prepare a big bandwidth, right? And that is
Exactly.
so I don't actually disagree with you. I just think that
can be accommodated in the framework. That would be your point.
Yes, right? It's a language.
Exactly.
It's a language.
Yeah.
You have to ask what's the right way of formulating it.
Right. And then you made this claim that you say working memory has a capacity of 2.5 bits. Now that's very contentious. Right? So what does it really mean, and on what do you base that statement?
Well, it's not my statement. It's actually the statement of brain scientists that call the particular type of memory working memory. It's basically a immediate decision-making framework, and they measure it by having to memorize sequences. So they get a memorized sequence. It's a particular definition that they use.
No, but it's contentious because in this case we're not talking about just strings of bits. Right, I can, in working memory, store your whole scene of blowing up this galaxy far away, right?
Yeah, but this is a blob. This is basically
no, but you see my point,
a pointer.
Right? The semantics of these chunks in my working memory can go way beyond
Absolutely.
what you can capture into. So we should be careful, certainly with young people in the room who are still innocent.
Right.
By saying working memory is 2.5 bits.
No, the working memory is not the whole basic whole library of knowledge behind that. It's just the chunk, the pointer.
Exactly.
Yeah.
Very good. Well, Daniel, thank you again for your great talk. So now we're going to enhance entropy of the coffee machine for about 15 minutes. Yeah. So be quick. Grab your coffee, relax, and then we have our presentation by Success Arcivala. Huh? What? Yeah.